Hello everyone, welcome back to learn about truss analysis. I'm Chaminder and today we are going to learn about how to analyze a truss using graphical approach. Mainly I'll discuss the procedure to analyze a truss using graphical approach in this video. When analyzing a truss using method of joints, there are two different approaches we can follow. One is graphical approach, the other one is analytical approach. Here we are going to learn how to analyze the truss using graphical approach. The key theory behind this approach is if a force system is in equilibrium, then its force polygon should be closed. When we are analyzing a structure, we are developing a Maxwell diagram to determine the truss member forces. Let's see how we can do that and how to analyze a truss using the graphical approach to determine its member forces. Okay, let's learn the procedure of this graphical approach to analyze the truss using this example. So you can see we have given a 7-member truss, one end with pin support and the other end is roller support, and 10 kilonewton external load is applied at top. Now what is the first thing we should do when analyzing any structure? As we learned before, we have to calculate the reaction forces first. So the first step of this method also to calculate the reaction forces using the three static equilibrium equations. For this structure, pin support, there are two reaction components, R1 and R2, and the roller support, one reaction force, that is R3. So using the three static equilibrium equations, we can calculate the unknown three reaction forces. That is the first step we should do. Then we have to label the truss according to the Bose notation. Before labeling, let's name all the joints of this truss. As you can see, I'll mark all the five joints as 1, 2, 3, 4 and 5. Then we need to start labeling the spaces between all the forces following the Bose notation. Now when we say all the forces, it will be external forces and member forces, which are internal forces. I'll start with the space between the external forces 10 kilonewton and R2. You can see the space between those two external forces, and I'll mark that space as A. And between the external forces 10 kilonewton and R3, we can mark that space as B. You can see in between those two forces, you can't see any other external force. So that is that region we can mark as a one space. So we mark it as B. Similarly, between R3 and R1, space between those two forces, I'll mark as C. And between R1 and R2, I'll label as D. Finally, the spaces between the members, we can mark it as E, F and G. So that's how you label your truss following the Bose notation. As you can see, we followed the space marking in a sequential order, and this is how it looks like at the end of labeling following the Bose notation. Also, we should know how to identify forces with respect to the Bose notation. So forces can be identified by the two labels on each side of it. For an example, the external load 10 kilonewton we can mark as FAB. Similarly, the member force of the member between joints 1 and 2 we can mark as FEA. So likewise, we should know how to identify the force with reference to the space labels. Now the third step is to start drawing vector polygons for joints. When we selecting a joint, the maximum number of unknown forces of that joint should be 2. For an example, if we consider joint 2, you can see a external horizontal load of 10 kilonewton acting in that joint, and two members are there, and it will create two unknown member forces and altogether 3 forces at that joint. So which means we can start drawing the vector polygon for joint 2. Likewise, if you check the other joints, you may find joint 3, there are 4 unknown member forces acting at joint 3, which we can't select to start drawing the vector polygon. Joint 5, 3 unknown member forces, and joint 1, 3 unknown member forces. But if you see joint 4, 2 unknown member forces and altogether 3 forces, because we know the reaction force R3, so which means we can select either joint 2 or joint 4 to start drawing the vector polygon or force polygon. One more thing, when we drawing the force polygon or the vector polygon, we should select appropriate scale. For an example, I can use to represent 2 kilonewton by 1 centimeter. And we should mention that when we drawing into a scale, what is the scale that we are using. So I'll start drawing the vector polygon, and I select joint 2 to start with. So joint 2 I'll start with. Okay, at joint 2 you can see 3 possible force components acting on that joint. One due to the external load 10 kilonewton, and one due to the member force of member 2, 3, and the third force due to the member force of member 1, 2. Okay, let's start drawing the forces one by one. So I'll start with 10 kilonewton meter, because that is the only force, only known force in that joint. So 10 kilonewton, I can represent it by 5 centimeters according to the scale that I used. So the force 10 kilonewton we can represent by the line AB. So the starting point is A, and I'll just mark A there, and 10 kilonewtons the arrow is in the towards the right side, the horizontal force. So I just mark 5 centimeters a horizontal line, and at the end of 5 centimeters I can mark as point B. Now AB representing the 10 kilonewton. Then we try to draw the force at joint 2 due to the member 2, 3. Here we don't know the magnitude of the internal force of that member. What we know is only the direction or the line of action of this force, that is a horizontal force. Since we can represent this load by BE at the diagram, in the diagram we know where the B is, and if we know the magnitude of that force, we can mark BE as a horizontal line. But since we don't know the magnitude, only we can mark the line of action. So that line of action should be a horizontal line through B. We can draw that line. So you can see it's a dotted line, red line. So our point E should be there anywhere in that red dotted line. We'll be able to find that point only by drawing the next force in the diagram. Right. Now we can draw the next force at joint 2. So that force is due to the member force of member 1, 2. Now what do we know about this member force? Like in the previous member, here again we don't know the magnitude. What we know, only the direction. So we can represent this force in the diagram by EA. We know the direction, it's a vertical force. Then we can mark that the line of action in the diagram, since we don't know the magnitude. So we know where the point A in the diagram. AE is a vertical line, so we can draw the vertical line just like this, going through the point A. So our point E should be somewhere in that vertical line. Hope you can remember when we draw the previous member force, the point E, we said it should be in that horizontal line too. Now hope you can understand where the point E is, because now in the previous one we said it should be in the horizontal line, and now we say point E should be in the somewhere in the vertical line. Then to satisfy the both cases, point E should be in the point where the two dotted lines intersect. So I can mark the point E like that. Right. Now this is the vector polygon for the joint 2. I think you may have noticed that I draw the member forces following the clockwise direction. In your case, you can either follow the clockwise direction or anti-clockwise direction, but make sure that you are following the same method throughout the joints that you are drawing to get all the member forces. Okay, what we can get it from this vector polygon diagram? We can get the magnitude and the direction of the forces acting at joint 2. Now, as I mentioned you before, you know how to mark the member forces using the space labels. So you can find that FAB is 10 kilonewton, AB 5 centimeters, and with the converting with the scale, you can find 5 into 2 kilonewton, it will be 10 kilonewton. Now what is FAB? FAB in the truss, it is the 10 kilonewton external load at joint 2. And what else we can get it? FBE. FBE is representing the member force of member 2, 3. Now BE, the length is 5 centimeters, which means the magnitude of the load is 10 kilonewton, and it is acting in the horizontal direction. Now why I put minus and say it is compression? That's because you can see when we say BE, BE is pushing the joint 2, which means that member is under compression. That's why I just make it minus 10 kilonewton, which represent the compression force. As we can see, A and E is the same point, which means the magnitude is 0. You know what is the information we can get it from that? That is the member force of member 1, 2 is 0. Since we have finished finding the unknown member forces at joint 2 by drawing the force polygon or the vector polygon, now we have to move to an adjacent joint and follow the step 3 to calculate the unknown member forces of the truss. Now again, when we selecting the adjacent joint, we should keep in mind that we have to select the joint where the maximum unknown forces at that joint should be 2. So if we consider joint 3 and joint 1, joint 3, since we know that the member force of member 3, 2, but we don't know the forces of 3 members, so we can't select joint 3. But joint 1, we know the member force of member 1, 2, and there are only 2 unknown member forces on members 1, 3 and 1, 5. We know the reaction forces R1, R2. So because of there is only 2 unknown forces, we can draw the vector polygon for joint 1 next. So likewise, we can repeat step 4 until all the members considered and all the member forces are, unknown member forces are calculated. And at the end, the diagram that we developed, that we called the Maxwell diagram. Here you can see the Maxwell diagram drawn for this example. And if you follow the procedure I explained you so far, you will be able to get this Maxwell diagram. Once you have the Maxwell diagram, you can obtain the member forces of that truss. This is the end of this video, and hope you learned the procedure to analyze a truss using the graphical approach. Thank you for watching.